Hey, how's it going, everybody out there in pre-cal world? Mr. Pike here, coming from C101, blasting live 1000 hertz of frequency to your computer. I don't know if that's the hertz or not, but let's go with it, 1000 hertz. Today we're going to be talking about 1.3, continuity and behavior. So when we think about the word continuity, all that is talking about is if we have a continuous function or not. And what a continuous function means, that pen doesn't work, is that it just continues, and I do not have to lift my pen or pencil, whatever you're writing with, and there is no break in the function at all. It just keeps going and going forever and ever. An example of a discontinuous function or a not continuous function would be something like 1 over x, where I cannot draw the entire graph without lifting my pencil. I have to lift the pencil from down here to up there. Also, there's an asymptote right there at x equals 0, so I cannot have a continuous function in this part. Now let's get to talking about these. One type of discontinuity that we have, notice here I have to lift up my pencil to continue graphing the function, so therefore they are not connected and they are discontinuous. This is called a jump discontinuity, or just jump. The graph jumps between distinct points. I have a point right here, wherever that may be. I also have a point up here, wherever that may be. I can see both of those points in my range, and there is a break between those points, so it jumps from one point to another. Okay, we also have something called an infinite discontinuity. Notice at my asymptote at x equals 0, I have a discontinuous function because it goes to negative infinity in that direction and goes to infinity in the other direction. So pretty much all we're looking for is if the graph goes to infinity in one or both directions. So in this example, like I said, it's going to infinity both sides. We could also have it such that it is going to infinity on both sides, but this is still an infinite discontinuity because these are not connected functions. They are not continuous functions. And the last type of discontinuity that we need to talk about is called removable discontinuity. Pretty much that is just a point that was removed from the graph. These are called holes. So if we have a hole at x equals c, where c is whatever x value it is, say that's 4 or 5 or whatever you want to call it, it continues and it looks like it has a continuous graph, but this point is actually not included. It is called a hole. So that would be a removable discontinuity because it was removed from the graph. Alright, so looking at our first example, it says if discontinuous, determine the type. But one way that we can check this is actually plug in the value for x. So if we have the square root of 8 plus 5, that is just the square root of 13, so that actually is a value right there. And if you were to look at the graph, this is the square root graph but moved left 5 because you have plus 5 on the inside, so 1, 2, 3, 4, 5, and it would do something like that. So when x is equal to 8, 1, 2, 3, 4, 5, 6, 7, 8, that is actually just going to continue through that point. So this is actually just a continuous function at that point. Alright, so looking at our first example, we have if discontinuous. Oh, this isn't our first example. We've already done one. Hello. Alright, so looking at our second example, I don't know, whatever example this is. Anyways, so with this one, notice we have a fraction. Do not forget, in a fraction, you can never have the denominator set to 0. So in this instance, I know for sure that this is going to be discontinuous at x equals negative 5. But if I plug in 5, I would have 25 minus 25 is 0. And 5 plus 5 is 10, so I'd have 0 over 10, so this would actually be 0 as your y value. So this one is continuous at that part. So what kind of discontinuity is this? Well, if you look at your graph for the function, this is just plugging it into the y equals, it looks something like that. So my guess is we would probably have a hole at negative 5. So if you want to even try to calculate the value at negative 5, you will notice that there is nothing for the y. Well, that is because there is a hole there, so there's not actually a value there. So I can say that this is a removable discontinuity. At x equals negative 5, and this is continuous at x equals 5. And that's all we need to see. All right, this is the last example that we are going to look at for continuity tests. So with this one, this is a piecewise function. So if you don't remember what that means, or you haven't seen it yet, pretty much all this means is at -2, we are going to have a split. We're going to have this graph when x is greater than -2, and this graph when x is less than or equal to -2. So that would look something, let's see, -2, we have x squared minus 1, so you're going to have a parabola that's moved down 1 when x is greater than -2. So at 1, it'll go something like that. And then it'll hit that point, and it is just less than, so I have an open dot there. I have a hole. And then the other half of this graph is x minus 5, so I just have a linear function when x minus 5 less than 2, so I'll start here and go down. Well, in just graphing that, that tells us what kind of discontinuity we have. This would be a jump discontinuity. Let's write that not that color. Jump, rope, no, not really. Unless you're feeling extra pizzazzy today. Don't ask me what it means, I don't know. Only the little gnomes running around in my head know. Yeah, at x equals -2. Cool. All right, looking at another example. This is a different kind of problem. In this one, we are going to, you can read the directions, obviously. Blah, 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 blah. So we have this interval, and we are looking for the zeros of this function. Well, what I've gone ahead and done is plug it into my equation. So you can see the y equals is our equation. And we can look at the graph. And then what I'm going to do is I'm going to hit second trace. So second, notice that little arrow appears right there. And if you hit trace, that's actually going to take you to calculate things. Second is the blue, so you're taking the blue part of it. And we can find the 0. So I'm going to go down, choose 0, I hit enter, and it says left bound. Well, I see that one of my zeros right here is about -1. So I'm going to say to the left of that would be -2, and hit enter. Notice that little arrow pops up right there, it is. And then it changes and it says right bound. Well, just to the right of that would be 0. And again, another little arrow pops up right there. It says guess, but I don't care because I know that it's somewhere. I don't know. I was going to come up with something funny, but it didn't happen. Anyways, so then you hit enter one more time, and it tells you the 0 is... Come on, calculator. There we go. -0.8004. So I can say that one of my zeros is x equals -0.800. This is also the coordinate point, 800, comma 0. And I can do the same thing to find the other one. So again, second calc, 0. And I'm going to do left bound on this one. Looks like it's about 1. Right bound would be 2. And between that would be 1.569. So we'd have 1.569, comma 0. Those would be your two zeros. Oh, but read the problem, Mr. Pike. Come on, come on. Determine between which consecutive integers the real 0 lie. Blah, blah, blah. I should have read the problem. So between which consecutive integers, this would be between -1 and 0. And this one would be between 1 and 2. That is really what we are looking for. I apologize. But hopefully you caught it. And you're like, what are you doing, Mr. Pike? You're crazy. Okay, I'm going to do one more of these, and I'm actually going to read the directions this time. Determine which consecutive integers the real zeros lie on the given interval. h of x equals x squared plus 4 over x minus 5 when the interval is -2 to 4. So again, I have graphed the picture. Make sure that when you go into your y equals, you put parentheses around the numerator and parentheses around the denominator. Otherwise, you will not get the same graph. So from -2 to 4, it looks like this actually is right here, and 4 would be right there. It never hits the x-axis. So easy peasy, we can say no x-intercepts. Actually, let's say no zeros. Let's use their terminology. No zeros, no zeros. I drew a 0 though. Alright, the next concept I want to talk about with you guys is called end behavior. Pretty much all that is talking about is what is the graph doing at the ends. So towards this end, or as x goes to -infinity or approaches -infinity, f of x, or your y value pretty much, is approaching infinity because it's going up forever. In the other direction, as x approaches infinity, so as x goes to infinity, f of x approaches infinity as well, because that is going up too. Okay, in your other example down here, you have as x approaches negative infinity. This part is always going to stay the same. It's always going to be as x approaches negative infinity and as x approaches infinity. It is only this part and any of your functions that will change. So same, and really that includes up to there, and this will change. That's what you're really going to have to think about. Okay, but on this one, as x approaches negative infinity, so if it goes to negative infinity, it looks like it's going up, so f of x is going to approach infinity. As x approaches infinity, so it goes that direction, f of x approaches negative infinity because that goes down and down and down forever. Another example that we could have is this one here, as x approaches negative infinity, so as it's going that way, it looks like this is an asymptote at 0, so it is going to keep getting closer and closer and closer to 0. Same thing in both directions. As x approaches infinity in that direction, it is also getting closer and closer and closer to 0. They can get closer and closer to numbers, they can get to infinity, they can get to 0, everything is possible. Alright, looking at this example, take a second, pause the video, write it down. Okay, so we're talking about describing the end behavior, so if you want to, you can go ahead and just take the time to list all this out. So as x approaches negative infinity, f of x approaches something, and as x approaches infinity, f of x also approaches something. Well, graphing it, looking at your y equals, it looks like it's going up to the left, going up to the right, so it is going to infinity in both directions. Cool. Alright, this next one messed up a little bit, so I'm having to go back and re-record this, so I apologize that there's all your stuff written on the page, so just ignore that. Yay. So doing the same thing, we are describing the end behavior of this function, and I'm going to go ahead and take my time. Ha! Took my time already. And I wrote as x approaches negative infinity, f of x approaches something, x approaches infinity, f of x approaches something. Okay, this graph, when we graph it, it looks something like this. So on the left-hand side, this is actually going to negative infinity, and that's going to positive infinity. So as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x also approaches infinity. Yay! Alright, looking at our last example of these notes. We have 5x squared plus 6 over x squared minus 1. Make sure you put parentheses in your y equals, otherwise these graphs will not come out. So make sure it looks like that, otherwise you'll get something cray-cray. So in looking at the graph of this function, we have something like this. So I can't really tell exactly what it's going to. However, we can make it easier by looking at the table. And if I continue on these numbers, you can see it's getting closer and closer to 7. Right? It's never going to touch 7. And if you look at your graph, you can kind of tell that it's going to keep going to 7 in both directions. Right? But it's a little bit hard to tell just off the mark, so that's why I went to the table to actually look what those values are getting closer and closer to. So with that decided, again, we need to write as x approaches negative infinity, f of x approaches 7. And, oops, as x approaches infinity, f of x approaches 7. 7 in both directions. Hopefully this video was helpful for you guys. If you have any questions, please ask one of your teachers or come ask me in C101. Bye-bye!